Okay, so this is part two of lecture 19, and as the slide highlights, it has to do with multivariate probability models. And multivariate, of course, means multiple variables. In fact, we already dealt with multiple variables. We spent a lot of time talking about n equals 2 and random variables x1 or x2, or equivalently x and y. Here we generalize things to n random variables, where the result is we have x1, x2, all the way up to xn. Xn could be 2, but in fact xn could be more. The material in this section is mostly conceptual in the sense that it extends our definitions of PDFs and CDFs and PMFs and marginals to arbitrary n. But in fact, it's not all that useful in terms of solving problems. You can only solve problems in kind of very structured, specialized cases. Still, we'll include the definitions just so that later on in the course, we'll be interested in things like a random variable W, which might be the sum of x1 plus x2 plus xn. And we'll be interested in properties of this sum, and it's just good to keep in mind that, in fact, there's a whole framework of definitions that describe the experiment that produces all n of these random variables. So here's our first definition. It's the multivariate joint CDF of x1 through xn. And this is just a generalization of the joint CDF of x1 and x2 of x1 and x2. The probability x1 is less than little x1 and x2 is less than little x2. Similarly, when the random variables are discrete, right, we have the joint PMF, and this joint PMF of n random variables is the generalization of the joint PMF of two random variables, x1 and x2, and it tells you the probability that the random variables takes on a particular set of values. For continuous random variables, here we have the joint PDF of x1 through xn. And once again, this is it's the n-way partial derivative of the joint CDF when n equals 2, we have the joint PDF of x1 and x2 is the partial with respect to x1 and x2 of the joint CDF. And this is just the generalization. So the joint PMF has exactly the same properties that you would have expected it to have. The joint PMF is always greater than 0. And the joint PMF, when you sum it over all possible values, it has to sum to 1, just as you learn for two random variables. Similarly, the joint PDF has exactly the same properties as for two random variables. The joint PDF is non-negative. You can find the joint CDF by integrating the PDF from minus infinity to xi over all random variables. And of course, the area under the curve in n dimensions, the integral of the joint PDF over all possible values, has to integrate to 1. And if you're interested in the probability of an event, it's exactly the same thing as we had before, whether we're interested in the discrete case or the continuous case. In the discrete case, if we're interested in whether x1 through xn satisfy some property and belong to a set A, we sum over all of the x's in the set A, we sum the probability to find the probability of A. And equivalently, in the continuous case, we integrate over the region A, the joint PDF of the random variables, to find the probability of A. It's exactly what we did in 2 dimensions, just generalized to n dimensions. In the next few slides are some examples that demonstrate some of these properties for some special cases where we can do the calculations. I'm going to skip those examples because I'm not planning on testing you on them, but I'll include them in the slide deck in case you're interested. The next important concept to recognize as being generalized when you have more than 2 random variables is the idea of a marginal PMF or PDF. In the case of discrete random variables, this example demonstrates, oh, we have a joint PMF of 4 random variables, W, X, Y, and Z. And perhaps you're just interested in the PMF of 3 of them, X, Y, and Z, and not W. And so now what you do is you simply sum the joint PMF over all W's, and that leaves you the marginal PMF of X, Y, and Z. So this idea generalizes in the sense that if, for instance, we're only interested in random variables W and Z, then we can sum the joint PMF of W, X, Y, and Z over both X and Y, right? And we're left with a PMF of the random variables we're interested in. So this is kind of a generalization of our earlier idea that, oh, if we had P of X and Y of X and Y, you could find Px of X by summing over all Y the joint PMF of X and Y. And so what's happening here is that you can take a PMF of many random variables and sum it over all of the random variables you don't care about, and you're left with a PMF of a subset of random variables. And all of these PMFs of subsets of random variables are considered marginal PMFs because they're not the PMF of all the random variables in the experiment. So the same thing happens for continuous random variables. So if we have a joint PDF of W, X, Y, and Z, if we integrate over all possible values of Z, then we're left with a joint PDF of W, X, and Y. If we integrate over all W and Y and Z, then we obtain the old friend, our PDF of X. The idea of independence also generalizes in the natural way that you would expect. The random variables x1 through xn are independent, right? If for all possible values x1 through xn, the joint PMF in the discrete case factors into the product of marginals, or the joint PDF in the continuous case factors into the product of marginal PDFs. So it's exactly the generalization of P of x1, x2 of x1, x2 being Px1 of x1, Px2 of x2, or in the continuous case, the joint PDF of x1, x2 being the product of the marginal PDFs. So the most important special case of independent random variables is the case when the x1 through xn are independent, but they're also identically distributed. And this we give the special designation IID. And in this case, it's the same as the definition for independence, but the only thing that's really different is that in each case, you'll see that x1 has PMF PX, x2 has PMF PX. All of the xn's have the same PMF. And in a continuous case, the joint PDF factors into the product of the marginals, and all of these marginal PDFs are identical. That's the idea of identically distributed. So in this example, random variables x1 through xn have a joint PDF that's equal to 1, subject to the constraint that each xi is between 0 and 1, and otherwise it's 0. And we're asked to find the probability of event A that the max of these xi's is less than or equal to a half. So the solution in the book solves this as a calculus problem by doing n-dimensional calculus to integrate over the region where all these xi's are less than or equal to a half. But in fact, the problem is hiding its structure. The structure is that, in fact, each xi has PDF that's equal to 1 for xi between 0 and 1 and 0 otherwise. And the joint PDF of x1 to xn is equal to the PDF of x1, PDF of x2, PDF of xn. And now I see I should have gone back and erased this subscript I, right? Because in fact, every xi has the PDF fx of x. So once you realize this fact, the rest of the problem is simple. The probability that the max over xi is less than or equal to a half is equal to the probability that x1 is less than or equal to a half, and x2 is less than or equal to a half, all the way up to xn is less than or equal to half. And then we use the fact that they are independent to say, well, this is the probability x1 is less than or equal to a half times the probability x2 is less than or equal to a half times all the way up to probability xn is less than or equal to a half. And then we recall that each one of these terms is in fact equal to 1/2 because the random variable x is uniform from 0 to 1. So in fact, we get 1/2 to the power n. As I said, the solution in the book treats this as a calculus problem. It just says, oh, we integrate over the region where each random variable is less than a half, and lo and behold, we get the same thing. To test whether you're comfortable with these ideas, try to solve this quiz. It looks kind of like the previous problem where we have a collection of random variables and we're interested in the probability that the max of these random variables is less than or equal to a half. But what's tricky about it is that in fact, this joint PDF has some extra conditions, like y1 has to be less than or equal to y2 and y3 has to be less than or equal to y4. What that tells you is that the joint PDF of the y's, those y's are not actually independent. They look as if they might be independent, but they're not. And you actually have to do the calculus to solve the problem. The next slide has the solution, and we'll stop here, and you can study it if you want to work this out.